Hello everyone, here is today's problem. AB are positive such that a cubed plus b cubed equals ab plus 1. We ask proof that the square of a minus b plus a plus b is at least 2. We are going to apply several techniques in inequalities, including AMGF inequality and Jensen inequality. So first of all, we know that a cubed plus b cubed plus 1 be greater than equals to 3ab times 1. And since a cubed plus b cubed equals to ab plus 1, ab plus 2 greater than equals to 3ab, which means that 2 greater than equals to 2ab, and therefore ab is less than or equals to 1. So this is the first inequality that we have using AMGM inequality. Next, we use a Jensen inequality. Note that a cubed plus b cubed over 2. Now we compare a cubed plus b cubed over 2 and a plus b over 2 power 3. Since the function y equals to x cubed is a convex function, hence the hand side is greater than or equals to the right hand side. Since a cubed plus b cubed equals to ab plus 1, so this is ab plus 1 over 2 greater than or equals to a plus b over 2 power 3. Since ab is less than or equals to 1, so ab plus 1 over 2 is less than or equals to 1. So this means that a plus b over 2 less than or equals to 1. Equivalently, a plus b is less than or equals to 2. So this is the second inequality we obtain, and this is using Jensen inequality. So these are the two important inequalities that we obtained so far. The product is at most 1 and the sum is at most 2. Now let S be the sum of AB, and therefore S is less than or equals to 2. Now let J to be A minus B squared plus A plus B minus 2. If we are able to show that this is greater than or equals to 0, then we prove the original inequality. So we hope that J is greater than or equals to 0. Why is this so? We will see that a minus b squared is equals a plus b squared minus 4ab. So this comes from here, and this can be written as s squared plus s minus 4ab minus 2. Since ab is less than or equals to 1, so this will be greater than or equals to s squared plus s minus 4 minus 2. So this is s squared plus s minus 6. And we can factorize as s minus 2, s plus 3. So initially, we hope that j is greater than or equals to 0. But since j equals to s minus 2 times s plus 3, s is positive and s is less than 2, it implies that this expression is less than or equals to 0. And from here, we are unable to tell whether j is positive or j is negative. So it seems that this attempt is not good enough. With this, we need to introduce another parameter. Let P to be the product of AB. From a cubed plus b cubed equals to ab plus 1, which means that this is a plus b. A squared plus b squared minus ab equals ab plus 1. And this can be written as a plus b squared minus 3ab. A plus b is s, and this is s squared minus 3p equals p plus 1. Then we have s cubed minus 3ps equals p plus 1, which means that p is equal to s power 3 minus 1 over 3s plus 1. And this is something that we need to use it later. So we still can use the previous result up to here. And AB equals to P. So we have s squared plus s minus 2 minus 4ab. AB equals to P, and it is s power 3 minus 1 over 3s plus 1. So we know that this is s minus 1, s plus 2. And when you combine this, this is 3s plus 1 minus 4. This is s minus 1, s squared plus s plus 1 over 3s plus 1. So j now equals s minus 1. This is 3s squared plus 7s plus 2 minus 4s squared minus 4s minus 4 over 3s plus 1. So this is s minus 1, negative s squared plus 3s minus 2 over 3s plus 1. S minus 1. This can be factorized as s minus 1, 2 minus s over 3s plus 1. Finally, it is s minus 1 squared, 2 minus s over 3s plus 1. S minus 1 squared is greater than equals to 0. 2 minus s is greater than equals to 0. And 3s plus 1 is positive. So j now is greater than or equals 0. Initially, we thought that using this method, we are able to show that j is greater than or equals to 0, but we failed. After introduce p equals ab and some algebra, we are now able to show that j indeed greater than or equals to 0. And this proves the original inequality. That's all for today's lesson. Hope you enjoyed it. I'll see you again next time. Bye bye.